Calculus 1 that first semester. And I could do that for a number of other courses or other pieces of information that I want to bring into my model. So I'm saying that I expect my college GPA to be a linear function, or at least to be approximated by a linear function of these different variables. When we do this, we make an assumption that there's no interaction between our predictor variables. So what I mean by interaction is that, for instance, we might think, and this is just a conjecture that I'm throwing out there, but perhaps students who have low test scores, ACT scores, might benefit more from participating in a learning community than students who had high test scores. I have no idea if that's true, but that's something we might be interested in looking at. And if we suspected that something like that were true, that's what we would call an interaction between test score and learning community. If that's the case, I need to put that into my model if my regression model is going to account for it. If I don't build an interaction term like that into my model will not take that into account. Now that can be a challenge because I've got 58 variables I have to think about. So if I were dealing with 3 or 5 variables, I could pretty easily come up with some plots and do some exploratory analysis to think about which interactions might be important to include in a model. But when I've got 58 variables, now I've got to think about 58 choose 2 possible two-way interactions, and then there's nothing saying I couldn't have interactions between 3 or more variables. So this becomes a challenge when I'm trying to fit a regression model in a situation like this. So that's multiple regression. Another form of regression, which you may have seen depending on which stats courses you've taken, is logistic regression. So a logistic regression model is one that I would use when my response variable only takes on 2 values. So when I only have 2 possible outcomes, such as the student left STEM or the student didn't leave STEM. And I build a logistic regression model in a way that's very similar to the way that I would build a multiple regression model, except that after I put together that function, I transform it into the interval 0, 1 using a logic function, which I won't talk about here. But it's a way to move from a linear function to a function whose outcomes are 0 and 1, and to estimate the probability of one of those events happening. But the important point I want to make when I talk about those regression models is that, again, they assume no interactions unless I explicitly build those into the model, and they assume that the response variable is connected to the predictor variables in some linear fashion. When I'm looking at my data set with my 58 predictor variables, I've already mentioned it becomes hard to account for interactions. And I'm not necessarily convinced that I have linear relationships. So random forest methodology pulls back on some of those assumptions. It allows me to be more free and make less restrictions on the relationship between my predictor and response variables, and therefore let the data really tell me the story. This is what's referred to as a non-parametric technique. I don't make any assumptions about the distribution, such as I'm not saying anything follows a normal distribution. To do this, as you might have guessed from the title, my forests are going to consist of growing trees. And I'll grow trees based on my predictor variables to try to predict a response. And I'll talk about how we grow the trees in a minute. So I've already alluded to some of the reasons why I think that random forest methodology is beneficial in a problem like I have. It doesn't require me to assume any linear relationships. It automatically handles interactions, whether I tell the model to look for them or not. Some other advantages and reasons why people use random forest are that they allow for a large number of predictor variables. So if you're working on maybe a genetics problem where you're trying to, it's not uncommon to have hundreds of thousands of predictor variables in some cases. Fitting a model to that can be a real challenge, but random forests can handle those kinds of things. It provides a measure of which predictor variables are most important. So I suspect out of these 58, there are probably some in there that are really important and really tell me which students are likely to leave and which aren't. And there are probably others that don't really matter at all. So if you talk about separating signal from noise, that's kind of what we're getting at here. Which of those 58 variables really drive at that signal that predicts which students are going to leave, versus the ones that don't? And random forests provide a way to measure how important each variable is, so I can see which ones are really driving the signal in these problems. Another advantage is that they can handle missing values. So I mentioned that survey that all the students are supposed to complete. Well, guess what? They don't all complete it. And so we have missing data. Sometimes maybe a student came in without taking the ACT or the SAT, so we don't have that kind of test data. That can be a challenge when we're fitting a regression model. There are ways that people go about handling that, but there are also built-in ways to handle that when we're working with random forests. So we grow a forest from first growing trees. And I've shown you an example of a single decision tree. So what I'm trying to do here is take all of my students, and so I think this is based on the 2014 incoming class, and I want to keep on splitting them into groups so that every time I split, the groups that end up in the same node are similar to one another, and the groups that end up in the other node are similar to one another, and meanwhile the two nodes themselves are as different from one another as possible. So I'll talk about how I make that happen in a minute, but before I do that, we'll just look through what's going on here. So in this case, our first split is based on high school GPA. So I'm saying if you had a GPA less than or equal to 3.46, you go this way. If your GPA was at 3.46 or above, you go this way. And then in that left-hand node, we split on ACT. In the right-hand node, we're splitting now on type of major. So we classified the majors into 5 categories, either human and health sciences, mathematical sciences, biological sciences, engineering, or physical sciences. And then we continue to split. So if I look at, based on what I'm seeing here, students who had less than a 3.46 GPA and an ACT greater than 23, there were 581 such students in that class, and 15% of them left STEM within their first year at Iowa State. So how did we decide these splits? So I mentioned we try to do it in a way that makes the cases in the same node similar to one another and makes the two nodes different than one another. So let's take a look at an example of how we would do that. So consider, in a real simple situation, suppose I only have 10 students sitting in some node, and I've listed their ACT scores here. So the lowest one was 20, the highest one was 33. In the Y row, 1 indicates the student left STEM, and 0 indicates the student didn't. So what I want to do is try to split up these students using only information on ACT in a way that makes the two nodes as different from one another as possible. So if you think for a minute how you might do that, one thing that jumps out at me is maybe I'll say, let's take these students who have the ACT less than 24, so take these 4 over here, put them in one node, and that way I got 3 out of 4 left in that node, and then I'll put everybody else in the other node, and that way I've got 5 out of 6 stayed. So I'm doing a pretty good job. I got one node where more of them are leaving, and one node where more of them are staying. Another option would be maybe I take these 7 on the left, put them into one node, so now I got 4 out of 7 leaving, and then take the other 3, put them on the right, and now I've got 0 out of 3 leaving there. So which of those is better? We need to some way evaluate which of those splits is the best way to do it. And the way that's typically done is for each case in the node we want to put it in, we subtract the y value minus the average y value and square it, and then add up those square deviations. So in this case I have 1, 0, 3/4 of them left, so I would take, for the one that was 0, I'd take 0 minus 3/4 and square it, and then for the other 3, my outcome is 1, so I'm going to take 1 minus 3/4 and square it, and add those up. And my goal is to minimize that sum of the square deviations between the two nodes. And if you go through and do the computation here, you see that if I use that first split on ACT of 24, I get a sum of square deviations of 1.583, and it's a little bit higher if I use the second one. So that tells me the best split, at least between these two, is this first one, splitting on 24. Yes, of course.
Does this method result in privileging splits that result in 2 roughly equal-sized groups rather than a lopsided group?
Not necessarily,
Okay.
no. You can specify that you're not going to allow it to split down farther than a certain amount, and that's something we may want to do to prevent overfitting. But unless I specify that, that doesn't necessarily happen. So then what we would do is we would take these new nodes that we got and we'd do the same thing, and we'd try to keep on splitting. And we would continue until either all the cases in our nodes are the same, have the same response, or we can't split anymore because they all look the same in terms of the predictor variables, or our nodes get so small that we've said we're not going to split any farther. And deciding how small you want to get, that's something I've done some research on, and it's really context dependent, but it is an important thing to think about, because if you split too small, you will overfit in a lot of cases. That means you'll start to model random noise rather than picking up the true signal. And so then when you go and apply your technique on a new data set, even though it looked like it was working great on your original one, it doesn't work so well on the new one. So that is something you have to be careful with. So now a new student comes along with a 3.81 GPA, a self-efficacy score of 22, that's from the MapWorth survey, and an ACT score of 28, and this is a bio major. So I want to predict, I want to know what's the probability of that student leaving. Well, all I got to do is trace through the tree. And in this case, that student, at least at this point, ends up in this node. So I would say, at least for right now, that student, I would estimate, has a 5% probability of leaving STEM within that first year. Now, individual trees are often what we call unstable. If I were to make just a small change in my original data, that would likely change all of the splits in the tree, and it could drastically change the prediction for the new case. So Bryman noticed this and set about to try to correct it. And his idea is, well, rather than making predictions based on just one tree, let's grow a whole bunch of trees and then average the predictions together to get something with less variance that's more stable. Now, of course, if that's going to be meaningful, then your trees have to be different. And he came up with 2 clever ways to do that. The first is, when we go to grow a tree, we don't just grow it on all of the students. We don't use all the students in our data set anymore. We take a sample, we take a random sample, and we do it with replacement. So some students might end up in there more than once, others might not end up in there at all. This is what we call a bootstrap sample. So each tree is grown from a different bootstrap sample. Now that also means that for each tree, there are some cases that don't come up at all in that tree. We call those out-of-bag cases, and that's helpful because we can use those cases to make predictions. So if I have a case that wasn't involved in growing that tree, then I can look and evaluate how well the tree does in predicting that case. So I'll get back to that idea. The second thing he does is when we consider a split, we don't look at all variables anymore. We only look at a randomly selected subset of them. So just as an example, if you consider, suppose I got 10 cases